Introduction. Hey kids, today we will learn equilibrium. Physical equilibrium involves a state of equilibrium of a system which undergoes phase transformation. For example, dissolution of salt, evaporation of water, etc. The equilibrium in chemical processes such as decomposition of calcium carbonate or reaction between hydrogen and iodine is called chemical equilibrium. The common physical equilibria are solid and liquid, liquid and gas, solid and gas. In homogeneous equilibria, the reactants and the products are in the same phase, whereas in chemical equilibria, the reactants and the products are in the different phase. So, throughout this module, we will learn equilibrium. Objectives. At the end of this lesson, you will be able to explain equilibrium in physical state, explain equilibrium in dissolution of solid or gases in liquids, explain chemical equilibrium, state law of chemical equilibrium, explain homogeneous equilibria, explain heterogeneous equilibria, discuss applications of equilibrium constant, discuss factors affecting equilibria. Equilibrium in physical state. When the concentration of reactant becomes constant, such that it does not change and the reaction appears to be stopped. The state of system in which no net change occurs is called equilibrium. Solid-liquid equilibrium. When a pure solid substance is heated, it starts changing into liquid at a certain temperature. At this temperature, the solid and liquid states of the substance coexist under the given conditions of pressure. For any pure substance, at atmospheric pressure, the temperature at which the solid and liquid states can coexist is called the normal melting point or the normal freezing point of the substance. At melting point, the solid substance is in equilibrium with liquid state of the substance. Let us consider ice and water at 273 Kelvin, melting point of ice, taken in a perfectly insulated thermos flask. An interesting feature of this system is that the temperature as well as the masses of ice and water remains constant. This represents a dynamic equilibrium between ice and water. As there is no change in mass of ice and water, so the number of molecules going from ice into water is equal to the number of molecules going from water into ice. Thus, at the equilibrium, rate of melting is equal to rate of freezing. Liquid-vapor equilibrium. To understand this equilibrium, let us take an example of evaporation of water in a closed vessel. When a small amount of water is taken in an evacuated vessel at room temperature, it starts evaporating. At first, the pressure inside the vessel increases. As the number of molecules in gas phase increases, it strikes the water surface and it gets captured. This is called condensation. The rate of condensation is less than rate of evaporation in beginning, but with increase in molecules of gas phase, the rate of condensation increases and it becomes equal to the rate of evaporation. At this state, the equilibrium is said to be established. Thus, at equilibrium, rate of evaporation is equal to rate of condensation. Solid-vapor equilibrium. The process of transformation directly from the solid phase to the gaseous phase without passing through an intermediate liquid phase is called sublimation. The reverse process, changing a gas directly into solid, is called deposition. For example, dry ice. Equilibrium involving dissolution of solid or gases in liquids. Solids in liquids. A solution in which no more solute particles can be dissolved is called saturated solution. For example, if we keep on adding sugar into water, then a stage comes when no more sugar dissolves into water. The saturated solution corresponds to state of equilibrium. When the rate of dissolution of sugar into liquid is equal to the rate of precipitation, then equilibrium is said to be established. This equilibrium is dynamic in nature. It can be demonstrated by adding some radioactive sugar into a saturated solution of non-radioactive sugar. it is observed that the solution and non-radioactive sugar also becomes radioactive. Gases in liquid. When a cold drink is opened, the carbon dioxide dissolved in it fizzes out rapidly. This represents an equilibrium situation. At a given pressure, there is equilibrium between the molecules of the solute in gaseous state and the molecules dissolved in the liquid. It can be expressed as effect of pressure on the solubility of a gas in a liquid is given by Henry's law. This law states that the mass of a gas dissolved in a given mass of a solvent at a given temperature is directly proportional to the pressure of the gas above the solvent. M is directly proportional to P. M is equal to Kp. The solubility of gas in a liquid decreases with increase in temperature. General characteristics of equilibria involving physical processes. At equilibrium, the measurable properties of the system becomes constant. At equilibrium, there is a dynamic balance between the two opposite processes. The equilibrium can only be attained in a closed system. When equilibrium is attained, there exists an expression involving the concentration of substances involved in equilibrium, which reaches a constant value at a given temperature. The magnitude of the constant value of the concentration indicates the extent to which the process proceeds before reaching equilibrium. Equilibrium in chemical processes. Dynamic equilibrium. The reactions in which products do not react to form reactants back are called irreversible reactions. For example, silver nitrate reacts with sodium chloride, gives rise to silver chloride and sodium nitrate. The reactions in which products react to form the reactants back are called reversible reactions. The reversible reactions are represented by putting two arrows pointing in opposite direction. For example, hydrogen reacts with iodine, gives rise to hydrogen iodide. The state at which there is no further change in concentration of reactants and product is called chemical equilibrium. At equilibrium, the rate of forward reaction is equal to rate of backward reaction. Chemical equilibrium is also dynamic in nature because reaction does not stop at equilibrium. The rates of forward and backward reaction being equal, the concentration of reactants and products remains constant. Let us illustrate the state of equilibrium with the help of example. Calcium carbonate, when heated to 1073 Kelvin in a closed evacuated vessel, starts decomposing to yield calcium oxide and carbon dioxide gas. Carbon dioxide builds up pressure. The pressure goes on increasing as the reaction proceeds and finally becomes constant and remains so long as the temperature remains constant. It appears as if the reaction has come to a stop, although CaCO3, calcium carbonate, is still present. This indicates that this system has attained the equilibrium state. Law of chemical equilibrium and equilibrium constant. The law of mass action states that at constant temperature, the rate of a chemical reaction is directly proportional to the product of the molar concentration of reacting species, with each concentration term raised to the power equal to the numerical coefficient of that species in the chemical equation. Let us consider a simple reversible reaction. The reactants A and B react to form the products C and D. The concentration in an equilibrium mixture are related as. Name it as equation 1. Equation 1 is called the equilibrium equation. Kc is called equilibrium constant. And the term is called the equilibrium constant expression. For a general reaction of the type, the expression for equilibrium constant can be written as, where C is subscript to K. That is, Kc is expressed in concentration of mole per liter. Law of chemical equilibrium can be stated as, at a given temperature, the ratio of product of equilibrium concentration of the products to that of the reactants, with each concentration term raised to the power equal to the respective stoichiometric coefficients in the balanced chemical equation has a constant value. Let the equilibrium constant for the reaction be Kc dash. Then the relation between Kc and Kc dash is Kc dash is equal to 1 by Kc. Homogeneous equilibria. In this equilibria, the reactants and products are in same phase. Equilibrium constant in gaseous system. For the reactions in which both reactants and products are in gaseous state, the equilibrium constant is expressed in terms of partial pressure. For these reactions, the equilibrium constant is denoted by Kp. The ideal gas equation is Pv is equal to nRT. P is equal to N by V RT, where P is pressure in Pascal, N is the number of moles of the gas, V is the volume in m cube, T is the temperature in Kelvin, and R is equal to 0.0831 bar liter per mole Kelvin. N by V can be expressed as concentration C in mole per liter and P is in bar. So, P is equal to CRT. For the general reaction, the value of Kp is where Pc, Pd, Pa, Pb are partial pressure of C, D, A and B respectively, and it can be solved to the relation between Kp and Kc is Kp is equal to Kc into RT raised to the power delta N, where delta N is equal to number of moles of gaseous products minus number of moles of gaseous reactants in the balanced chemical equation. Pressure is expressed in bar. Heterogeneous equilibria. The equilibria in which the substances involved are present in different phases is called heterogeneous equilibria. For example, when liquid is in equilibrium with gas as shown below, the equilibrium constant is the concentration of pure liquid is 1, that is, H2O in liquid form is equal to 1. Hence, applications of equilibrium constant. Characteristics of equilibrium constant. The value of equilibrium constant is independent of initial concentrations of reacting species. The value of equilibrium constant changes with change in temperature. For a reversible reaction, the equilibrium constant for a backward reaction is inverse of the equilibrium constant for the forward reaction. The equilibrium constant is independent of the presence of catalyst. If equilibrium constant is expressed in terms of concentration, it has different units for different reactions. Predicting the extent of a reaction. The magnitude of equilibrium constant tells us about the extent to which the reactants are converted into the products before the equilibrium is attained. Predicting the direction of the reaction. The reaction quotient Q measures the relative amount of products and reactants present during a reaction at a particular point in time. It is denoted by Qc with molar concentration and Qp with partial pressures. For a general reaction, if Qc greater than Kc, the net reaction is taking place in backward direction, that is direction of reactants. If Qc less than Kc, the net reaction is taking place in forward direction, that is direction of products. If Qc is equal to Kc, the reaction is at equilibrium, that is no net reaction is taking place. Calculating equilibrium concentrations. Write chemical equation for the equilibrium. Write equilibrium constant expression for the reaction. Express all unknown concentrations in terms of a single variable x. Substitute the equilibrium concentrations in terms of x in the equilibrium constant expression. Solve the equation for x. Substitute the value obtained for x in the expressions in the step 3 to calculate equilibrium concentrations. Relationship between equilibrium constant K, reaction quotient Q and Gibbs energy G, the energy freely available from the system at particular set of condition which can be put into useful work is called Gibbs energy. The relation is, name it as equation 1, where it represents standard Gibbs energy. We know that at equilibrium Q is equal to K and delta G is equal to 0 from equation 1. Rearranging gives. This equation relates the standard Gibbs free energy change to the temperature and equilibrium constant. The equilibrium constant is, if change in standard Gibbs free energy is greater than 0, then K is less than 1, making the backward reaction feasible. If change in standard Gibbs free energy is less than 0, then K is greater than 1, making the forward reaction feasible. Factors affecting equilibria. The effect of parameters such as concentration, temperature, pressure can be studied with the help of Le Chatelier's principle. It states that if a system at equilibrium is subjected to a change of concentration, pressure or temperature, the equilibrium shifts in the direction that tends to undo the effect of the change. Effect of concentration change. According to Le Chatelier's principle, when the concentration of the substance in a system at equilibrium is increased, then the equilibrium will shift so as to use the substance added. Suppose at equilibrium, one of the reactants is added. The equilibrium will shift in the forward direction to consume the reactants. On the other hand, if one of the products is added, the equilibrium will shift in the backward direction to consume the products. For example, on a humid day, we sweat more. The sweating on a humid day is more because surrounding air has large amount of water vapors and our body cannot lose water at water vapors. Factors affecting equilibria. Effect of pressure change. According to Le Chatelier's principle, increase of external pressure should affect the equilibrium in such a way as to reduce the pressure. This implies that the equilibrium will shift in the direction which has smaller number of moles of the gaseous substances. For example, if we increase the pressure, the volume occupied by the system decreases and the number of molecules per unit volume increases. This effect can be counterbalanced if the equilibrium shifts in a direction involving less number of moles. So, increase in pressure in this case will favor the forward reaction. Effect of inert gas addition. At constant volume, the inert gas increases the total pressure of the system, but the partial pressure of the reactant and product remains same and the equilibrium remains undisturbed. At constant pressure, the addition of inert gas will increase the volume. So, to counterbalance this effect, the equilibrium will shift to the side where number of moles are increased. For example, the addition of inert gas at constant pressure will push the equilibrium to the backward direction. Effect of temperature change. A chemical equilibrium involves two reactions, one favoring the product and other favoring the reactant. If one reaction is exothermic, the other must be endothermic. For example, the forward reaction is exothermic and backward reaction is endothermic. Now, if the temperature is increased, then the equilibrium favors backward direction as it tends to undo the effect of added heat. If temperature is decreased, the equilibrium will shift in forward direction. So, low temperature favors the formation of ammonia. Effect of a catalyst. The presence of a catalyst does not disturb the state of equilibrium because it increases the rate of forward as well as backward reaction to the same extent. The reaction of formation of ammonia can be carried out at high temperature because high temperature favors backward reaction. They have to be maintained at low temperature, but at low temperature, the rate of reaction is very slow and it takes very long to attain the equilibrium. To increase the rate of reaction, catalysts are used. so that equilibrium is attained early. Did you know? A research team led by Dr. Diego Donzes, an assistant professor in the Department of Aerospace Engineering, has been awarded $2.2 million by the Air Force Office of Scientific Research AFOSR to study the complex interaction of turbulent flows in the presence of thermal non-equilibrium. The Basic Research Initiative BRI award is given to study thermal and mechanical non-equilibrium effects on turbulent flows, in particular the fundamental mechanisms for energy exchanges through direct numerical simulations, molecular simulations and experiments. Summary. Let us summarize what we have learned. When the concentration of reactant becomes constant such that it does not change and the reaction appears to be stopped, this state of system in which no net change occurs is called equilibrium. At melting point, the solid substance is in equilibrium with liquid state of the substance. In equilibrium between liquid and vapor state, rate of evaporation is equal to rate of condensation. The direct conversion from solid phase to the gaseous phase is called sublimation, and the reverse of it is called deposition. A solution is said to be saturated if no more solute particles can be dissolved. The law of mass action states that at constant temperature, the rate of a chemical reaction is directly proportional to the product of the molar concentration of reacting species, with each concentration term raised to the power equal to the numerical coefficient of that species in the chemical equation. If the reactants and the products are in the same phase, then the equilibrium established is called homogeneous equilibria. The equilibria in which the substances involved are present in different phases is called heterogeneous equilibria. The relationship between equilibrium constant K, reaction quotient Q, and Gibbs energy G is factors affecting equilibria are concentration change, pressure change, inert gas addition, temperature change, effect of catalyst.